For over a century, physicists told us nothing travels faster than light. It was the ultimate law, carved into the foundation of reality itself. But in laboratories right now, particles are doing exactly what Einstein said was impossible. They communicate instantly across any distance. Recent experiments prove it beyond doubt. Scientists have even begun building devices that could bend space itself. What we thought was forbidden might actually be the key to everything. If you enjoy learning about the cutting edge of physics, hit that subscribe button. Prepare yourselves. We begin. Light moves at 186,000 miles per second. Nothing in our universe can go faster. This is not a suggestion. It is the iron law of physics, written into the fabric of reality by Einstein in 1905. Every experiment we have ever conducted confirms it. Every particle accelerator, every cosmic ray, every photon racing through space obeys this limit without exception. But why does this boundary exist at all? Einstein discovered something profound about the nature of time itself. When you move faster, time slows down for you compared to someone standing still. This effect is tiny at normal speeds, but as you approach light speed, it becomes extreme. At 90% light speed, time runs at less than half its normal rate. At 99%, time crawls. At exactly light speed, time stops completely. This creates a mathematical wall. To push an object with mass all the way to light speed would require infinite energy. The universe simply does not contain enough fuel. Even a single grain of sand would need more energy than our entire galaxy produces in a year. This is why physicists were so certain the speed limit was absolute. Einstein proved this through his theory of special relativity. Space and time are not separate. They form a single fabric called space-time. When you move through space, you are also moving through time. The faster you go through space, the slower you go through time. Light speed is the point where these two movements balance perfectly. It is the cosmic speed limit because it is built into the geometry of space-time itself. But there was something Einstein noticed right away, something that troubled him deeply. His equations revealed that information could never travel faster than light. If it did, causality would break. You could receive a message before it was sent. You could know the future. Cause and effect would become meaningless. The universe would descend into paradox. For decades, this seemed to settle the matter completely. Nothing can outrun light. The universe has spoken. But Einstein himself found something that challenged this certainty. In 1935, he published a thought experiment that revealed a crack in the foundation. Quantum mechanics, the theory describing the smallest particles, seemed to allow instant connections across space. Not just fast connections, instant ones. Einstein thought this proved quantum mechanics was incomplete. He believed there had to be a deeper theory that would restore the speed limit. He spent the rest of his life searching for it. Most physicists dismissed his concerns. They called him stubborn, unable to accept the new physics. What they did not realize was that Einstein had discovered something real, something that would shake physics to its core 30 years after his death. The question waiting in the shadows was simple but terrifying. What if the speed limit could be broken after all? In the quantum world, particles do something impossible. Two particles can become connected in such a way that measuring one instantly affects the other, no matter how far apart they are. Physicists call this phenomenon entanglement. It has been confirmed in laboratories thousands of times. This is not speculation. It is verified fact. Here is how it works. Create a pair of entangled particles. Send one to Tokyo and keep the other in New York. When you measure a property of your particle in New York, the particle in Tokyo instantly knows and responds. Not after a delay. Not after light has time to travel between them. Instantly. The connection happens faster than light could possibly travel between the two cities. Scientists first created entangled particles in the 1970s. The experiments were crude but successful. Today we can entangle particles routinely. We can separate them by miles and watch them maintain their connection. In 2016, China launched a satellite that created entangled photons and sent them to ground stations over 700 miles apart. The particles remained connected. When one was measured, its partner responded immediately. This feels wrong. Your intuition tells you something must be traveling between the particles. Some signal, some messenger carrying information at light speed or slower, but decades of experiments prove otherwise. There is no signal, no messenger, no delay whatsoever. The connection is genuinely instantaneous. Albert Einstein called this spooky action at a distance. He hated it. It violated everything he believed about how the universe should work. In his view, nothing could influence anything else faster than light. The speed limit was sacred, but quantum mechanics seemed to ignore his law completely. The strangest part is what happens when you try to use entanglement to send messages. You cannot. The measurements on both sides appear random. Only when you compare the results later, traveling at normal speed, do you see the correlation. The universe allows instant influence but blocks instant communication. It is as if reality found a loophole in its own rules. Physicists initially thought entanglement might be an illusion. Perhaps the particles agreed on their properties beforehand when they were created together. They could be like twins who agreed to always wear matching shirts. When you see one wearing red, you instantly know the other is also wearing red. No faster than light influence needed, just a prior agreement. This explanation seemed reasonable. It saved the speed limit. It made sense, but it was about to be completely destroyed by a theorem that would change physics forever. One man would prove that this comfortable explanation cannot possibly be true. In 1964, a physicist named John Bell proved something extraordinary. He showed that quantum entanglement cannot be explained by any prior agreement between particles. The connection must be genuinely faster than light. There is no way around it. His proof was mathematical and absolute. Bell was not trying to overthrow physics. He was a quiet man working at CERN who had been troubled by quantum mechanics since his student days. The Copenhagen interpretation, the standard explanation taught in textbooks, never satisfied him. It seemed vague and incomplete. So during a sabbatical year, he decided to examine the old debates between Einstein and Niels Bohr. What he discovered shocked him. Bell realized that Einstein's concerns were completely valid. More than that, Bell saw something nobody else had noticed. You could actually test whether quantum mechanics was truly non-local through a simple experiment, not a thought experiment, a real one you could perform in a laboratory. Here is the key insight. Take two entangled particles and measure them along different axes. You can rotate your measuring device to different angles. If the particles decided their properties beforehand, there is a limit to how often their measurements can disagree. Bell calculated this limit mathematically. It comes out to at least 33% disagreement when you measure along different directions. But quantum mechanics predicts something different. It says the disagreement rate should be 25%. This is a clear, testable difference. Run the experiment. Count how often the measurements disagree. If you get 33% or more, the particles made prior agreements. If you get 25%, the influence really is instantaneous. Scientists ran this experiment in the 1970s and 80s. They used photons, which are particles of light, because they are easier to entangle and measure. The equipment was challenging to build. The measurements had to be incredibly precise. Any error could ruin the results. The answer came back clear and unmistakable. 25% disagreement. Exactly what quantum mechanics predicted. The experiment has been repeated hundreds of times with increasingly sophisticated equipment. The result never changes. Some recent experiments have closed every possible loophole that might explain the results in other ways. Bell's theorem proves that quantum mechanics is fundamentally non-local. Faster-than-light influences are real. They exist in our universe right now, confirmed by mountains of experimental evidence. Einstein was wrong to think locality could be saved. The speed limit he worked so hard to establish has a genuine exception built into the laws of nature. But this creates an enormous puzzle. How can faster-than-light influences exist without destroying causality? How does the universe prevent paradoxes? The answer involves one of the strangest restrictions ever discovered in physics. 30 years before Bell proved his theorem, Einstein had already identified the exact problem. In 1935, he published a paper with two colleagues, Boris Podolsky and Nathan Rosen. It became known as the EPR paper after their initials. This paper would haunt quantum mechanics for decades. Einstein proposed a thought experiment. Imagine creating two particles that must have opposite properties to conserve some physical quantity. Send them flying apart in opposite directions. According to quantum mechanics, neither particle has a definite property until you measure it. They exist in a superposition, doing all possibilities at once. Now measure the first particle. Instantly, it collapses to one specific property. But here is the problem. The second particle, which could be miles away, must instantly collapse to the opposite property. Otherwise, the conservation law gets violated. But how does the second particle know what happened to the first one? The information must travel faster than light. Einstein presented this as proof that quantum mechanics was incomplete. He believed the particles must have definite properties all along, even before measurement. There had to be hidden variables, secret instructions that each particle carried with it. These hidden variables would explain the correlations without requiring faster-than-light communication. The paper caused a sensation. The New York Times ran it on the front page. Einstein was the most famous scientist alive, and he was challenging the new quantum theory that everyone else thought was settled. The physics community split. Some supported Einstein. Most sided with Bohr, who defended quantum mechanics fiercely. Bohr published a response, but it was confusing and difficult to understand. Even today, physicists debate what Bohr actually meant. He seemed to be saying that the measurement of one particle and the state of the other particle were somehow the same event, even across distance. This did not really address Einstein's concern about faster-than-light influence. For decades, the debate seemed purely philosophical. Both interpretations made the same predictions for experiments. How could you test the difference? You could not. The question appeared untestable. Many physicists dismissed it as meaningless metaphysics. They adopted a shut up and calculate attitude. Quantum mechanics gives the right answers. Stop asking what it means. Einstein died in 1955, still convinced that quantum mechanics was wrong. Most physicists thought he had wasted his final decades on a pointless crusade. He seemed like an old man unable to accept new ideas. But Einstein had been right all along. He had identified a genuine mystery at the heart of physics. The mystery stayed buried until Bell came along. He proved that Einstein's local hidden variable theory makes different predictions than quantum mechanics. You could test it. And when scientists finally did, they discovered something disturbing. Einstein's intuition about locality was wrong, but his concern about quantum mechanics was completely justified. What comes next reveals exactly how measurement creates these impossible connections. When you measure a quantum particle, something dramatic happens. The particle suddenly snaps from doing many things at once to doing just one thing. Physicists call this the collapse of the wave function. Before measurement, the particle is described by a wave of probabilities spread across space. After measurement, all those probabilities vanish, except one. The particle has chosen. This collapse is the most mysterious event in physics. Nobody fully understands how or why it happens. We just know that it does. Every time we look at a quantum system, we find it in one definite state. The act of observation forces reality to make a choice. For entangled particles, this collapse links across space instantly. Measure one particle, and you force both to collapse together, maintaining their correlation. The wave function does not collapse separately for each particle. It collapses as a single, unified object, even when the particles are miles apart. This unified collapse is what creates the faster-than-light connection. Think about how strange this really is. The wave function is not a physical thing like a wave in water. It is a mathematical object, a description of probabilities. Yet when you perform a measurement here, this mathematical description changes instantly everywhere, including at distant locations where the entangled partner sits. Some physicists argue that the wave function represents our knowledge, not physical reality. In this view, the collapse just represents us learning new information. But Bell's theorem proves this interpretation fails. The correlations are too strong to be explained by learning. Something physical must be connecting the particles. Other physicists suggest measurement is not special. The measuring device itself is just another quantum system that becomes entangled with the particle. In this view, there is no true collapse. The wave function just keeps growing, entangling more and more objects. But then why do we see definite results? Why does the world appear classical and certain rather than quantum and fuzzy? The Copenhagen interpretation says we should not ask these questions. Just accept that measurement causes collapse and move on. Calculate the probabilities. Make predictions. This approach works brilliantly for practical purposes. Engineers use it to build quantum computers and other devices. But it leaves the fundamental mystery untouched. What we know for certain is this. Entangled particles maintain correlations that require instant coordination across space. The measurement of one particle determines what the other particle will be found to be, no matter the distance. This is confirmed fact, repeated in laboratories worldwide. The speed of light limit has an exception carved right into quantum mechanics. But if particles can influence each other faster than light, why can we not use this to send messages? Why can we not exploit entanglement for instant communication? The answer reveals another strange restriction woven into quantum mechanics, one that saves the universe from complete paradox. Miguel Alcubierre was a physics graduate student in 1994 when he figured out how to break the light speed barrier without actually breaking any laws. His solution was elegant and shocking. Instead of moving through space, you warp space itself. If space-time can bend, you can surf on that bending and travel faster than light would move through flat space. Einstein's equations for general relativity describe how mass and energy curve space-time. Alcubierre realized you could also curve space-time with a specific configuration of exotic matter. Create a bubble around your spacecraft, contract space in front of the ship, and expand space behind it. The ship itself stays stationary relative to the space inside the bubble, so it never exceeds light speed locally. But the bubble slides through space faster than light. Picture a surfboard on an ocean wave. The board does not move faster than water. It rides the wave, which carries it forward. The Alcubierre drive works the same way. Space itself moves, carrying the ship along for the ride. From the perspective of someone inside, time flows normally. You feel no acceleration, no crushing g-forces. You sit comfortably while space-time does all the work. The numbers are staggering. With the right warp bubble geometry, you could theoretically reach any speed. 10 times light speed, 100 times, 1,000 times. There is no built-in limit. You could cross the Milky Way galaxy in weeks instead of tens of thousands of years. Reaching nearby stars becomes a matter of days. But there is a catch. Actually, several catches. To create the warp bubble, you need exotic matter with negative energy density. This is not regular matter. Regular matter has positive energy. You need the opposite. You need something that pushes space-time outward instead of pulling it inward. And you need a lot of it. Early calculations suggested you would need more negative energy than the mass energy of the entire visible universe. That requirement made the Alcubierre drive seem like pure fantasy. Negative energy sounded like made-up nonsense. Most physicists dismissed the idea as a fun mathematical curiosity with no connection to reality. Space opera writers loved it. Scientists moved on to more practical problems. But here is where the story gets interesting. Negative energy might not be impossible after all. Quantum mechanics predicts something called the Casimir effect, and this effect has been measured in laboratories. It proves that negative energy exists in our universe, not just as theory, as verified physical fact. The question suddenly shifted. The Alcubierre drive might not violate physics. It might just require technology we do not yet have. And in the years since Alcubierre published his paper, physicists have found ways to drastically reduce the energy requirements. Some calculations now suggest you might only need the mass energy of a large planet. Still enormous, but not impossible. Not anymore. The next challenge is understanding exactly what negative energy is and whether we can ever produce enough of it. Imagine folding a sheet of paper so two distant points touch. Poke a hole through both spots. You have created a shortcut. Travel through the hole and you instantly jump from one location to the other without crossing all the space in between. This is the basic idea of a wormhole. Wormholes are solutions to Einstein's equations. They are not science fiction. They are mathematically possible structures allowed by general relativity. A wormhole is essentially a tunnel through space-time connecting two different regions. Enter one end, called a mouth, and emerge from the other mouth, which could be light years away. The journey through the tunnel might be only a few miles. Think about what this means for faster-than-light travel. You are not actually moving faster than light. You are taking a shortcut through a different part of space-time. Light traveling the long way through normal space would take years. You traveling through the wormhole arrive in seconds. From your perspective, you never broke the speed limit. You just found a better path. Einstein himself discovered the possibility of wormholes in 1935, working with Nathan Rosen. They called them Einstein-Rosen bridges, but they assumed these bridges would be useless for travel. The calculations showed they would collapse before anything could pass through. The tunnel would snap shut faster than light could cross it. Later work showed Einstein was too pessimistic. If you thread the wormhole with exotic matter, you can hold it open. That exotic matter would need negative energy density, just like the Alcubierre drive requires. This connection is not a coincidence. Both methods cheat the light speed limit by manipulating space-time, and both need the same impossible ingredient. Wormholes might also allow time travel under certain conditions. If one mouth of the wormhole moves at high speed while the other stays still, time dilation causes them to age differently. Step through, and you might emerge in your own past. This creates all the paradoxes you would expect. You could meet yourself. You could prevent your own birth. Physics does not yet know whether such paradoxes mean time travel is impossible or whether the universe has some way of preventing contradictions. Some physicists think microscopic wormholes might exist naturally in the quantum foam of spacetime at the smallest scales. These would be far too tiny to travel through. Each one would be much smaller than an atomic nucleus. But their existence would prove that wormholes are physically real, not just mathematical abstractions. No one has ever observed a wormhole. We have no idea how to create one. The energy requirements appear impossibly large, but the mathematics says they are allowed. General relativity does not forbid them. They might exist somewhere in the universe right now. The real question is whether exotic matter with negative energy can exist in large enough quantities to make wormholes and warp drives practical. Recent discoveries suggest the answer might be yes. Every object you have ever encountered has positive energy. Your body has energy from the bonds between atoms and the motion of molecules. Stars have energy from fusion reactions. Even empty space has energy from quantum fluctuations. Positive energy is everywhere. Negative energy is the opposite. It would push on space-time instead of pulling. It would repel rather than attract. Most importantly, it would curve space-time in the opposite direction from normal matter. This makes it essential for faster-than-light travel because you need to expand space in certain regions to create a warp drive or hold open a wormhole. The problem is that negative energy seems forbidden by basic physics. Energy density tells you how much energy exists in a given volume. For normal matter, this number is always positive. This makes intuitive sense. Matter has mass. Mass has energy through Einstein's equation, E equals mc squared. Energy is positive. Therefore, matter should have positive energy density. For a long time, physicists thought this was an absolute rule. Some even tried to prove theorems showing that negative energy density must be impossible. If you could create negative energy, it might violate the laws of thermodynamics. You could potentially extract infinite energy from empty space. You could build a perpetual motion machine. The universe would break. There are also strange consequences for stability. Objects with negative energy would accelerate in the opposite direction when pushed. A ball rolling downhill would roll uphill instead. Throw it, and it would fly backward toward you. Gravity would repel negative energy objects instead of attracting them. This seems to violate everything we know about how physics works. But quantum mechanics changes the situation completely. At the quantum level, space is not empty. Virtual particles constantly pop into existence and disappear. These quantum fluctuations fill every cubic inch of the universe. They give empty space a baseline energy density. This is called vacuum energy or zero-point energy. Here is the crucial part. If you can reduce the vacuum energy in a region below its natural level, you have created negative energy density relative to normal empty space. The total energy is still positive when you include the rest of the universe. But locally, in that specific region, the energy density is lower than it should be. Mathematically, this shows up as negative. This trick turns out to be possible. Quantum mechanics allows certain configurations where the vacuum energy gets squeezed or depleted. The effect is tiny. The negative energy density you can create is minuscule, but it is real. It has been measured. It exists. The question becomes whether you can generate enough negative energy to power a warp drive or stabilize a wormhole. The amounts required are staggering. We are talking about negative energy densities larger than the positive energy density of an atomic nucleus. This seems impossibly far beyond what quantum mechanics might provide. Yet, recent theoretical work suggests ways to amplify these effects. The situation is not as hopeless as it first appeared. What seemed like a fundamental barrier might be a difficult engineering problem instead. In 1948, Dutch physicist Hendrik Casimir predicted something bizarre. Place two uncharged metal plates very close together in a vacuum. Quantum fluctuations in the space between the plates would create a force pushing the plates together. This force would arise from nowhere. Empty space would spontaneously push on the metal. The explanation involves quantum mechanics. The vacuum is filled with virtual photons that appear and vanish constantly. These fluctuations have all possible wavelengths. Between the plates, only certain wavelengths fit. Outside the plates, all wavelengths exist. This means there are more virtual photons pushing the plates together from outside than pushing them apart from inside. The imbalance creates a net force. This force is incredibly weak. For plates separated by 1 micrometer, roughly 1/100th the width of a human hair, the pressure is only about 1/100th of an atmosphere. You need extremely sensitive equipment to detect it. But in 1997, physicist Steve Lamoureux measured the Casimir force with high precision. It matched the theoretical prediction exactly. This experimental confirmation proved something revolutionary. The energy density between the plates is lower than the energy density of empty space far from the plates. You have created a region of negative energy density. It is real. It is measurable. It exists in laboratories on Earth right now. The Casimir effect shows that quantum mechanics naturally produces regions of negative energy under certain conditions. This validates the basic principle behind warp drives and wormholes. Negative energy is not forbidden. It is a confirmed feature of our universe. But there is a massive gap between the tiny negative energy of the Casimir effect and the enormous amounts required for manipulating space-time. The negative energy density between Casimir plates is about 1/10,000th of a joule per cubic meter. To hold open a wormhole big enough for a person, you would need negative energy densities trillions of times larger. Some physicists have proposed ways to amplify the effect. Use moving mirrors to squeeze more vacuum energy out of a region. Use curved surfaces to change how virtual particles behave. Use quantum fields in excited states to enhance the imbalance. None of these suggestions are proven. They are speculative ideas based on our incomplete understanding of quantum field theory. There is also a concerning limit. The more negative energy you try to create, the more unstable the system becomes. Quantum fluctuations fight back. Some calculations suggest there might be hard caps on how much negative energy can exist in any given volume. These caps might prevent us from ever building warp drives or wormholes, no matter how advanced our technology becomes. Still, the existence of the Casimir effect changed the conversation. Faster than light travel went from impossible in principle to maybe possible with future technology. That is an enormous shift. It means scientists can study these ideas seriously instead of dismissing them as fantasy. And some scientists are doing exactly that. They are running experiments to test whether we can push the boundaries of negative energy production further than anyone thought possible. At NASA's Johnson Space Center, researchers are attempting something extraordinary. They are trying to create measurable distortions in space-time using laboratory equipment, not theoretical calculations. Actual experiments with real hardware. If successful, this work could represent the first tiny step toward practical faster-than-light travel. Harold White leads the team. In 2011, he published a paper showing that the energy requirements for an Alcubierre drive might be much lower than originally thought. By carefully shaping the warp bubble, you could potentially reduce the exotic matter needed from the mass of Jupiter to something closer to the mass of a space probe, still enormous, but millions of times smaller than previous estimates. This finding motivated NASA to fund actual experiments. White and his team built a device called the White-Juday Warp Field Interferometer. The goal is to detect tiny distortions in space-time caused by a specialized capacitor arrangement. They are not trying to build a working warp drive. They are testing whether they can produce even the faintest hint of the space-time geometry that a warp drive would require. The device uses an interferometer which splits a laser beam into two paths and then recombines them. If one path goes through a region of warped space-time, even slightly, the light will take a different amount of time to traverse that path. When the beams recombine, they will be slightly out of phase. This creates an interference pattern that reveals the space-time distortion. In 2013, White announced they had detected anomalous readings. The interferometer showed a signature consistent with a tiny warp field. The effect was incredibly small, but it was there. Other scientists immediately raised concerns. Were they really seeing space-time warping? Or were they measuring instrument noise and thermal fluctuations? The results were right at the edge of what the equipment could detect. Subsequent attempts to replicate the findings have produced mixed results. Some experiments show similar anomalies, others show nothing. The scientific community remains skeptical. Extraordinary claims require extraordinary evidence, and these results are barely above the noise floor. More precise experiments with better controlled conditions are needed. But even the attempt represents progress. NASA taking this seriously signals that faster-than-light concepts have moved from pure speculation into the realm of testable science. Peer-reviewed papers discuss the physics. Engineers design equipment. Experiments run. This is how new technologies begin, with small steps in obscure laboratories. Another group at the Advanced Propulsion Lab has explored using laser pulses to perturb the quantum vacuum and create temporary regions of negative energy density. They are investigating whether intense electromagnetic fields can squeeze vacuum fluctuations in ways that might be useful for propulsion. Results so far are inconclusive, but the research continues. The work faces enormous challenges. Even if you can create a warp field signature, scaling it up by the trillions of times needed for actual propulsion seems impossible with known physics. You would need not just negative energy, but enormous amounts of it, concentrated and controlled with precision we cannot currently imagine. Still, 50 years ago, most scientists thought negative energy was impossible. Now we know it exists. 20 years ago, warp drives required more energy than the visible universe contains. Now maybe they only need planetary-scale energy. Progress is slow but real. The question is not whether the physics allows faster than light travel. The physics clearly does. The question is whether we can ever build the engineering to exploit it. In laboratories around the world, scientists are routinely teleporting quantum information from one location to another. Not science fiction, not distant future technology. This is happening right now, today. Particles on one side of a room have their quantum states transferred to particles on the other side without anything physical crossing the gap. Quantum teleportation uses entanglement to transmit the complete quantum state of a particle. Here is how it works. Start with two entangled particles. Keep one and send the other to a distant location. Now take a third particle whose state you want to teleport. Perform a special measurement that entangles this particle with your half of the original entangled pair. This measurement destroys the quantum state you wanted to teleport. You can no longer access that information locally. But the measurement gives you two classical bits of information. Send those bits through normal channels to the distant location at light speed or slower. When they arrive, the person there uses that information to transform their entangled particle. That particle now has the exact quantum state that your original particle had. The quantum information has been teleported. The state vanished from one location and reappeared at another. Nothing physical carrying that state traveled between them. The entangled pair provided a quantum channel. The classical bits provided the instructions for reconstruction. Together, these elements achieved teleportation. The first successful demonstration happened in 1997 at the University of Innsbruck in Austria. They teleported the quantum state of a photon across a laboratory bench. Since then, the distances have grown dramatically. In 2017, China used their quantum satellite to teleport photon states from Tibet to a space station orbiting Earth, a distance of nearly 900 miles. This has enormous implications for quantum computing and quantum communication. You can transfer delicate quantum information without it degrading as it travels through fiber optic cables or air. You can build quantum networks where information moves by teleportation rather than transmission. These networks would be essentially unhackable because entanglement prevents anyone from intercepting the quantum state without destroying it. But quantum teleportation does not let you send messages faster than light. You still need to transmit those classical bits, which can only move at light speed. Without those bits, the person at the distant end cannot extract the teleported information. Their particle is entangled but appears completely random until they receive the instructions for decoding it. This limitation is built into quantum mechanics at a fundamental level. Information can be destroyed locally and reconstructed remotely using entanglement. But you cannot skip the light speed step of sending classical data. The universe gives you something amazing, but make sure you cannot use it to break causality. Some researchers are exploring whether you might be able to teleport more than just quantum information. Could you teleport actual particles? Could you teleport molecules? Could you, in principle, teleport a person? The answer is that nothing in known physics forbids this, but the practical challenges are absurd. You would need to measure and transmit the quantum state of every single particle in a human body. That is about 7 octillion atoms. The data requirements would be staggering beyond comprehension. Yet, the fact that scientists seriously discuss such possibilities shows how far quantum teleportation has come. What seemed impossible 30 years ago is routine today. The boundaries keep shifting. What seems impossible now might be routine 50 years from now. The universe has built in a strange asymmetry. quantum correlations propagate instantly across any distance. This is confirmed fact. But useful information, the kind you could use to send a message, cannot travel faster than light. This is also confirmed fact. Both statements are true simultaneously, and understanding why requires careful thought. When two particles are entangled, measuring one immediately affects the probability distribution of the other. This correlation is real and instantaneous. But when you measure your particle, the outcome is random. You get plus or minus with 50-50 probability. You have no control over which result appears. This randomness is essential. Now think about what this means for the distant particle. Before your measurement, it has a certain probability distribution. After your measurement, its probabilities change to be correlated with your result. But from the perspective of the person at that distant location, nothing appears to change. Their particle still looks completely random. They cannot tell whether your measurement has happened yet. Only when they receive a classical message from you, traveling at light speed, can they compare their results to yours and see the correlation. The correlation was there all along, but detecting it requires information from both locations. That information cannot travel faster than light. This is why you cannot use entanglement for faster than light communication. You can affect the distant particle, but the effect is hidden in randomness. You cannot encode a message in purely random data. There is nothing to read. The correlations only become visible after the fact, when classical information brings the two measurement records together. Some people suggest clever schemes to work around this. What if you measure in different bases? What if you use multiple entangled pairs? What if you pre-program the measurements? Physicists have examined every conceivable trick. None of them work. Quantum mechanics always prevents you from extracting faster than light messages from entanglement. The no communication theorem proves this mathematically. This restriction saves the universe from paradoxes. If you could send messages faster than light, you could send them backward in time according to some observers. Special relativity shows that different reference frames disagree about the order of events separated by space-like intervals. Faster than light messages would let you exploit these disagreements to create closed loops of causality. You could receive your own messages before you sent them. Quantum mechanics walks a knife edge. It allows non-local correlations that Einstein thought should be impossible, but it blocks communication in exactly the way needed to prevent paradoxes. This seems almost too convenient. How does nature enforce this boundary so precisely? Why can influence propagate instantly, while messages cannot? The answer lies in the structure of quantum mechanics itself. The wave function describes all possibilities simultaneously. Measurement collapses this to one outcome, but that collapse happens everywhere at once for entangled systems. This global collapse is non-local. However, the randomness of quantum measurements prevents you from exploiting the non-locality for communication. The same theory that creates faster than light correlations also guarantees you cannot use them to send information. This delicate balance is one of the deepest mysteries in physics. Most physicists accept it as a brute fact about how nature works, but a few wonder whether there might be something deeper, some principle we have not yet discovered that explains why the universe chose this particular balance between locality and non-locality. The speed of light does not just limit how fast things can move. It protects the structure of causality itself. To understand why, you need to think about time dilation and what it means for cause and effect. Every speed limit in physics exists to prevent something more fundamental from breaking. When you move close to light speed, time slows down for you compared to stationary observers. This effect has been measured with atomic clocks on airplanes and satellites. It is not theory, it is tested fact. At 99% light speed, time runs about 7 times slower for you. At 99.9%, it slows by a factor of 22. As you approach light speed, time crawls nearly to a stop. Now imagine traveling faster than light. Say you somehow reach twice light speed. According to the equations of relativity, time dilation becomes imaginary. Not imaginary, as in make-believe. Imaginary as in involving the square root of -1. The math breaks. Time no longer behaves like time. The future and past mix together in ways that destroy meaning. Different observers, moving at different speeds, already disagree about simultaneity. Events that look simultaneous to you happen at different times to someone moving past. This is fine as long as no information travels faster than light. Everyone can agree on cause and effect, even though they disagree about exact timing. But allow faster than light messages, and this breaks down completely. Here is a specific example. Say you are on Earth, and your friend is on a spaceship moving away at 90% light speed. You send an instant message to the ship. From your perspective, it arrives at the same moment you sent it. But from the perspective of someone moving even faster in a different direction, your message arrives before you sent it. They see the effect preceding the cause. If your message says, change your plans, and your friend changes course based on it, then you created a situation where the effect happened first. To some observers, the ship changed course for no reason, and only later did you send the message explaining why. This violates the fundamental principle that causes must precede effects. The speed of light limit prevents these paradoxes. By forbidding faster than light travel and communication, physics ensures that all observers can agree on causal order. You might disagree about how much time passed between cause and effect, but you will always agree on which came first. This is what locality really protects. Not some arbitrary speed limit, but the logical structure of cause and effect. Quantum entanglement threatens this structure by allowing instant correlations. But as we saw earlier, those correlations cannot carry messages. They cannot be used to manipulate cause and effect. The universe allows non-locality, but only in a form that preserves causality. It is as if nature is walking a tightrope, permitting just enough weirdness to make quantum mechanics work while preventing full paradox. Some interpretations of quantum mechanics try to eliminate this tension entirely. They argue that maybe the speed limit is not fundamental after all, or that causality works differently than we assume. These ideas remain highly controversial, but the fact that serious physicists consider them shows how troubled the foundations of modern physics really are. What seems certain is this: if we ever develop true faster-than-light travel, we will need to completely rethink what time means and how causality operates. The universe might permit it, but the cost could be abandoning concepts we thought were bedrock. In 1967, physicist Gerald Feinberg proposed a strange possibility. What if certain particles can only exist while moving faster than light? Not particles that accelerate past light speed, but particles that are always faster, born fast. These hypothetical particles are called tachyons. Tachyons have bizarre properties. As they lose energy, they speed up. As they gain energy, they slow down. But they can never slow all the way down to light speed, because that would require infinite energy, just as accelerating a normal particle to light speed does. Light speed is a boundary that neither type can cross. Normal matter always slower, tachyons always faster. From a mathematical perspective, tachyons have imaginary mass. Not zero mass, like photons, but the square root of -1 times some real value. This sounds absurd, but the equations of relativity allow it. Imaginary mass would give particles unusual properties that keep them perpetually above light speed. Whether such particles actually exist is an entirely different question. If tachyons are real, they would be extremely difficult to detect. They move so fast that they might cross a detector before the detector can register them. They would also emit Cherenkov radiation continuously as they plow through the quantum vacuum faster than light can propagate through it. This energy loss would make them slow down, which paradoxically means speeding up further. Tachyons would behave opposite to our intuitions. The bigger problem is causality. A tachyon moving from point A to point B travels faster than light. To some observers, in different reference frames, it would appear to move backward in time, You could use tachyons to send messages to your own past. Build 2 tachyon transmitters and you have a time machine. The grandfather paradoxes emerge immediately. Most physicists believe tachyons do not exist precisely because of these causality problems. The universe seems to forbid them. Every search for tachyons has come up empty. Particle accelerators have never produced them. Cosmic rays show no evidence of them. If they existed and interacted with normal matter, we should have seen them by now. Some theories of particle physics, particularly older versions of string theory, initially predicted tachyons would exist. When calculations showed that these theories contained tachyons, physicists took it as a sign that something was wrong with the theory. The equations needed adjustment. Tachyons were viewed as a bug to be fixed, not a feature to embrace. But there is a loophole. Suppose tachyons exist but cannot interact with normal matter. They would pass through our detectors without leaving any trace. They would be completely invisible. Some physicists have speculated that dark matter might be composed of tachyons or other exotic faster-than-light particles. This idea remains highly speculative, and most scientists find it implausible. The deeper question is whether physics can ever allow particles that travel faster than light without destroying causality. Tachyons seem to say no. Their very existence creates paradoxes, but quantum mechanics already has faster-than-light correlations. Maybe with the right framework, tachyons could exist without paradoxes too. Nobody knows for sure. For now, tachyons remain theoretical curiosities. They show that faster-than-light particles are not mathematically impossible, just physically problematic. Whether that problem is fatal or just a puzzle waiting to be solved remains unknown. The universe itself is expanding. Space stretches everywhere, all the time. Galaxies embedded in this expanding space move apart from each other, and at large enough distances, they recede faster than the speed of light. This is not forbidden. It does not violate relativity. And it is happening right now throughout the cosmos. The expansion of space is different from motion through space. When a rocket accelerates, it pushes against space-time and moves from one location to another. Einstein's speed limit applies to this kind of motion. But space itself can stretch, carrying galaxies along with it. The galaxies themselves stay roughly stationary within their local patch of space. But the patches grow, increasing the distance between galaxies. Think of it like dots on the surface of an inflating balloon. As the balloon expands, the dots move apart. None of the dots are actually moving along the surface. The surface itself is growing. If the balloon inflates fast enough, dots far apart from each other will separate faster than light could travel across the balloon's surface. This is exactly what happens in the universe. Galaxies very far away are receding from us faster than light, not because they are moving through space at that speed, but because the space between us and them is expanding so rapidly that the total rate of separation exceeds light speed. Light leaving those galaxies right now will never reach us. It is fighting against the expansion and losing. We can observe this through redshift. When galaxies move away from us, their light gets stretched to longer wavelengths. The faster the recession, the more the light shifts toward the red end of the spectrum. For the most distant galaxies, the redshift is so extreme that visible light gets stretched into infrared or even radio waves. The current expansion rate of the universe is about 42 miles per second per million light-years. This means that for every million light-years of distance, space expands by 42 miles every second close by. This rate is tiny, but at distances of billions of light-years, it adds up to faster than light recession speeds. General relativity allows this without any contradiction. The speed of light limit only applies to local motion through space. It says nothing about how fast space itself can expand. There is no law preventing space-time from stretching at any rate. In fact, during the very early universe, space expanded much faster than it does now. Some scientists initially worried this created paradoxes. If galaxies can recede faster than light, can they send light signals that arrive instantaneously or even backward in time? The answer is no. light from those galaxies still travels at light speed through local space. The expansion just means that light can never bridge certain distances. The observable universe has a boundary beyond which we can never see, no matter how long we wait. This expansion has practical implications for faster-than-light travel. Even if you could build a warp drive and travel to a distant galaxy, you would be fighting the expansion of space. The universe is pulling your destination away from you at an ever-increasing rate. For galaxies far enough away, no propulsion system could overcome the expansion. They are forever out of reach. Unless you could travel faster than the expansion rate itself, then you might be able to catch up to fleeing galaxies. This would require warp drives capable of many times the speed of light. Whether such extreme warping is possible remains unknown, but the universe shows us that faster-than-light recession is already built into the cosmos. In the first tiny fraction of a second after the Big Bang, the universe expanded faster than light, much faster. Space stretched exponentially, doubling in size every infinitesimal instant. This period of cosmic inflation lasted less than a trillionth of a second. But in that brief moment, the universe grew by a factor of at least 10 to the 26th power. Possibly much more. Inflation was proposed in 1980 by physicist Alan Guth to solve several puzzles about the early universe. Why is the universe so uniform in all directions? Why is space so geometrically flat? Why do we not see magnetic monopoles or other exotic particles that should have been created in the Big Bang? Inflation answers all these questions elegantly by postulating a period of insanely rapid expansion. During inflation, space expanded much faster than the speed of light. Regions that were once close enough to interact were suddenly separated by vast distances. Light could not keep up. This explains why the universe looks the same in all directions. The visible universe today came from a tiny patch that was once small enough to reach equilibrium before inflation blew it up to cosmic scales. The expansion rate during inflation was staggering. Space doubled in size every 10 to the negative 37 seconds or so. That is an incomprehensibly short time. In just 100 doublings, a region the size of a proton would expand to the size of the observable universe. The actual inflation likely involved many more doublings than that. This faster-than-light expansion does not violate relativity for the same reason that ordinary cosmological expansion does not. Space itself is stretching. Nothing is moving through space faster than light locally. But globally, the distance between points can grow at any rate. General relativity permits this without contradiction. Inflation explains several otherwise mysterious features of the universe. But it also raises new questions. What caused inflation to start? What caused it to stop? The leading theory involves quantum fields permeating space. These fields start in a high-energy state that drives rapid expansion. Eventually, the fields decay to a lower energy state, and inflation ends. The energy released by this decay creates all the matter and radiation we see today. Evidence for inflation comes from precision measurements of the cosmic microwave background radiation. This ancient light shows tiny fluctuations in temperature across the sky. The pattern of these fluctuations matches what inflation predicts. Alternative theories struggle to explain the data as well. Most cosmologists now accept inflation as the best explanation for the early universe. Some versions of inflation predict that it never completely ends. Different regions of space stop inflating at different times, creating separate pocket universes. Our observable universe would be just one pocket in an eternally inflating multiverse. In this scenario, the universe is far larger than we can ever observe, with countless regions beyond our horizon. If inflation happened once, it could happen again. Some physicists speculate that advanced civilizations might learn to trigger localized inflation. Create a bubble of rapidly expanding space, and you could build new universes or travel to distant regions of our own universe by creating shortcuts through expanding space. These ideas are highly speculative, but they are based on the same physics that describes the early universe. The key takeaway is that faster-than-light expansion is not just permitted by physics. It already happened. The universe proved that space-time can stretch at any rate. The laws of physics allow it. The only question is whether intelligence can ever learn to control it. The expansion of the universe is speeding up. This discovery, made in 1998, shocked physicists. Everyone expected expansion to be slowing down due to gravity pulling galaxies together. Instead, observations of distant supernovae showed that galaxies are flying apart faster and faster. Something is pushing them. That something is called dark energy. Nobody knows what it is. We only know it exists because of its effect on cosmic expansion. Dark energy makes up about 68% of all energy in the universe. It is the dominant component of reality, and we have no idea what it is or where it comes from. Dark energy behaves opposite to normal matter and normal energy. Gravity pulls things together. Dark energy pushes things apart. As the universe expands, the density of normal matter decreases because particles spread out over larger volumes. But dark energy density stays constant. More space means more dark energy. This causes the expansion rate to accelerate over time. Right now, the acceleration is modest. The universe is expanding about 9% faster than it was 7 billion years ago. But this acceleration is increasing. In the far future, dark energy will dominate completely. Galaxies will recede from each other at exponentially growing rates. Eventually, everything beyond our local group of galaxies will disappear beyond the cosmic horizon, receding faster than light can travel through space. Dark energy might be the energy of empty space itself. Quantum field theory predicts that the vacuum should have energy. Virtual particles popping in and out of existence contribute to the energy density of empty space. Calculate this using quantum mechanics, and you get a prediction. Unfortunately, that prediction is wrong by about 120 orders of magnitude. This is the worst prediction in the history of physics. Something is clearly missing from our understanding. Either quantum mechanics is wrong about vacuum energy, or there is some unknown mechanism that cancels out most of it, leaving just the tiny amount we observe as dark energy. Both possibilities suggest our current theories are incomplete at a deep level. Another possibility is that dark energy is not constant but changes over time. Maybe it is a field, like the one that drove inflation, but currently in a different state. This field could evolve, causing dark energy to strengthen or weaken over billions of years. Some theories predict dark energy will eventually fade away. Others predict it will keep growing until it tears apart galaxies, solar systems, even atoms in a final apocalypse called the Big Rip. Dark energy affects the possibility of faster-than-light travel in an important way. If you could build a warp drive, you would be fighting against cosmic expansion. Dark energy makes the problem worse because it accelerates that expansion. Distant galaxies are not just moving away, they are moving away faster and faster. Catching up to them requires overcoming an ever-increasing headwind. On the other hand, if we could understand and control dark energy, it might provide the key to manipulating space-time. Dark energy already curves space-time in exotic ways. Learning to harness it could give us the exotic matter and negative energy needed for warp drives and wormholes. This is pure speculation, but dark energy clearly shows that the universe contains large amounts of something that works opposite to ordinary matter. The discovery of dark energy fundamentally changed cosmology. It revealed that we do not understand most of the universe. The stuff we can see and measure, normal matter and radiation, makes up only about 5% of reality. The rest is dark matter and dark energy, mysterious components that we detect only through their gravitational effects. Faster than light expansion driven by dark energy is happening everywhere, all the time, pulling the cosmos apart at accelerating rates. There is a sphere around Earth that marks the edge of what we can ever see. Beyond this boundary, galaxies exist, but their light will never reach us. The expansion of space carries them away faster than their light can travel toward us. This creates a fundamental horizon in the universe. No matter how long we wait or how powerful our telescopes become, we cannot see past it. The observable universe has a radius of about 46 billion light-years. This seems wrong at first. The universe is only 13.8 billion years old. Light has only had that much time to travel. So why can we see objects 46 billion light-years away? The answer is expansion. Light left those distant galaxies 13 billion years ago when they were much closer. While the light traveled toward us, space expanded, carrying those galaxies farther away. By the time their ancient light reaches us today, they are 46 billion light-years distant. But many galaxies are farther than 46 billion light-years away. We cannot see them because their light has not had time to reach us yet. Some of that light is on its way and will arrive in the future. But for galaxies beyond a certain distance, their light will never arrive. The expansion of space is winning. Those photons are losing ground despite traveling at light speed through local space. This creates a cosmic horizon similar to the event horizon of a black hole. Just as nothing can escape from inside a black hole's event horizon, nothing can reach us from beyond our cosmic horizon. Information from those regions is permanently cut off. They might as well be in a separate universe. The situation gets worse over time. Dark energy is accelerating the expansion. This means the cosmic horizon is actually shrinking. Galaxies that we can see today will eventually disappear from view as they cross our horizon. In the far future, an astronomer looking at the sky will see fewer and fewer galaxies. Eventually, only our local cluster will remain visible. The rest of the universe will have receded beyond reach. This has profound implications. There could be infinitely many galaxies beyond our horizon. We have no way to know. The universe might be infinite in size, or it might be finite but larger than we can ever observe. Both possibilities are consistent with what we see. We are trapped inside an observational bubble that is shrinking due to accelerating expansion. Some physicists wonder if this horizon is as absolute as it seems. Quantum mechanics might allow information from beyond the horizon to leak through in subtle ways. Entangled particles could potentially connect regions that are causally disconnected by expansion. This remains highly speculative, but it suggests that horizons in physics might not be completely impenetrable barriers. For faster-than-light travel, cosmic horizons represent the ultimate challenge. Even if you could build a perfect warp drive, you could not reach galaxies beyond the horizon. They are receding too fast. You would need to travel faster than the expansion rate, which for the most distant regions means many times the speed of light. Whether physics allows such extreme speeds remains unknown. The cosmic horizon reminds us of how little of reality we can access. Most of the universe is forever beyond our reach, unless we develop technology that lets us cheat the expansion itself. There is an alternative to the Copenhagen interpretation that resolves the measurement problem in a radical way. It is called pilot wave theory, or Bohmian mechanics, after physicist David Bohm, who developed it in the 1950s. In this interpretation, particles always have definite positions and velocities. There is no collapse, no randomness. Everything is deterministic. But this determinism comes at a cost. The theory requires a wave that guides each particle, telling it where to go. This pilot wave fills all of space and evolves according to the Schrödinger equation. The particle rides the wave like a surfer rides ocean waves. The pilot wave determines the particle's motion completely, even though we cannot predict it because we cannot know the exact initial conditions. Here is the shocking part. The pilot wave is non-local. It responds instantly to changes anywhere in space. When you measure one entangled particle, the pilot wave for both particles changes immediately, everywhere. This is how pilot wave theory explains quantum correlations without collapse. The particles themselves never influence each other faster than light. but the wave guiding them does. This makes pilot wave theory explicitly non-local in a way that even the Copenhagen interpretation tries to avoid. Bohm embraced this non-locality. He argued that the universe must have faster than light connections at a fundamental level. These connections are hidden from us because we cannot directly observe the pilot wave. We only see particles which obey local laws. The non-locality operates in the background, invisible but essential. Many physicists rejected pilot wave theory for exactly this reason. They found the explicit, faster-than-light influences unacceptable. Others dismissed it because it does not make different predictions than standard quantum mechanics. If two theories predict the same experimental results, why choose the more complicated one? The Copenhagen interpretation was simpler. It became the default. But pilot wave theory has advantages. It eliminates the measurement problem. There is no collapse because particles always have definite properties. Measurement just reveals what was already there. This makes the theory more intuitive in some ways. Reality exists independently of observation, which matches our everyday experience. The theory also extends naturally to quantum field theory and can describe particle creation and annihilation. It handles relativistic quantum mechanics, though the non-locality becomes more problematic in that context. Some versions of the theory require a preferred reference frame, which conflicts with the spirit of relativity, if not the letter. John Bell favored pilot wave theory. He saw it as proof that alternatives to Copenhagen were possible. The physics community had been taught that Copenhagen was the only consistent interpretation. Bell showed this was false. Other interpretations exist and work just as well. This opened the door to rethinking the foundations of quantum mechanics. Pilot wave theory remains a minority view. Most physicists still use Copenhagen for practical calculations, but the theory has gained supporters in recent decades. Some experiments have even visualized pilot wave-like behavior in fluids, where droplets bounce on a vibrating surface and exhibit quantum-like phenomena. This does not prove pilot waves are real in quantum mechanics, but it shows the concept is physically reasonable. The key insight is that non-locality might not be a bug, but a feature. Maybe the universe really does have faster-than-light connections woven into its fabric. Maybe locality is an approximation that breaks down at the quantum level. Pilot wave theory suggests this is not just possible, but necessary to explain what we observe. What if measurement does not collapse the wave function? What if all possible outcomes happen and you simply experience one branch? This is the many worlds interpretation proposed by physicist Hugh Everett in 1957. In this view, the universe constantly splits into parallel branches every time a quantum measurement occurs. Here is how it resolves the faster-than-light problem. When you measure an entangled particle, you do not force it to choose one outcome. Both outcomes happen. The universe splits. There is now a version of you who measured plus and a version who measured minus. Each version lives in a separate branch of reality that cannot communicate with the other. The distant entangled particle also splits. In the branch where you measured plus, the distant particle is minus. In the branch where you measured minus, the distant particle is plus. The correlations are perfect because the branching is coordinated, but no information travels between the particles. The split happens everywhere at once throughout the wave function. This eliminates the need for faster-than-light influence. The particles do not communicate. They do not need to. The wave function already contains both possibilities. Measurement just determines which branch you end up in. From your perspective, it looks like the distant particle responded instantly to your measurement. But really, both results existed all along in different branches. Many worlds is completely local in this sense. No information travels faster than light. Cause and effect work normally within each branch. The appearance of non-locality comes from the fact that you cannot see the other branches. If you could see the full wave function, you would see that everything evolves according to local laws. But this comes at an enormous philosophical cost. you must accept that every quantum measurement creates vast numbers of parallel universes. Every time a particle decays or does not decay, the universe splits. Every time a photon goes through a left slit or a right slit, reality branches. The number of branches grows exponentially fast. After just a few seconds, there are more branches than atoms in the observable universe. Most physicists find this extravagant. The theory multiplies entities beyond necessity. Why accept countless unobservable universes just to avoid wave function collapse? Copenhagen may be mysterious, but at least it does not require infinite parallel realities. Supporters of many worlds argue the opposite. Copenhagen requires something extra, the collapse mechanism. Many worlds just takes the Schrödinger equation seriously and follows it wherever it leads. Nothing needs to be added. Collapse is the extra assumption, not branching. The math naturally describes splitting universes. Why fight it? Many worlds has grown more popular in recent decades. About 20% of physicists now favor it, according to surveys. Younger physicists especially find it appealing. It treats measurement as just another physical process, not something special that requires new laws. It unifies quantum and classical physics under one framework. The interpretation also has practical advantages for thinking about quantum computing. In many worlds, a quantum computer explores all possible solutions simultaneously across different branches. This is exactly how quantum algorithms work mathematically. Many worlds provides an intuitive picture of what the computer is doing. For faster-than-light travel, many worlds has interesting implications. If the universe is constantly branching, then faster-than-light travel might just move you between branches rather than backward in time. The paradoxes dissolve because you never return to your original branch. You cannot kill your grandfather because that would happen in a different branch. Your existence remains consistent within your branch. This is speculative, but it shows how different interpretations of quantum mechanics lead to different views on what faster-than-light travel would mean. Maybe locality is not fundamental. Maybe it emerges from deeper structures we do not yet understand. Many worlds suggests one possible answer. A particle encounters a barrier it does not have enough energy to cross. Classical physics says it bounces back. Quantum mechanics says it can pass through anyway. This is called quantum tunneling, and it happens constantly throughout nature. Radioactive decay depends on it. So does the fusion in stars. Without tunneling, the universe would be a very different place. Tunneling occurs because particles are described by wave functions. These waves do not stop abruptly at barriers. They decay exponentially inside the barrier, but some of the wave leaks through to the other side. There is a small probability the particle will be found on the far side, having tunneled through without ever being inside the barrier classically. The strange part is how long tunneling takes. Several experiments have tried to measure the tunneling time. Some results suggest it happens instantaneously. The particle disappears from one side and appears on the other with zero time delay. Other experiments give different answers, depending on exactly what you measure. The tunneling time might not even be a well-defined concept. If tunneling is truly instantaneous, this creates problems. A particle tunneling through a thick barrier would cross that distance in zero time. Divide distance by zero and you get infinite speed. The particle would have traveled faster than light. But no information travels because tunneling is probabilistic. You cannot control when or where particles tunnel. You cannot send messages through barriers using tunneling. Some physicists argue that tunneling does take time, just very little time. The wave function shifts gradually from one side to the other. What looks instantaneous is actually extremely fast, but still finite. This interpretation avoids the faster-than-light problem, but requires careful definitions of what you mean by the particle's position during tunneling. Tunneling becomes more likely when barriers are thin and when particle energies are close to the barrier height. For very thick or very tall barriers, the tunneling probability drops exponentially. This is why macroscopic objects never tunnel through walls. The probability is absurdly tiny. But for individual atoms or electrons facing atomic-scale barriers, tunneling happens routinely. Scanning tunneling microscopes exploit this effect. They bring a sharp metal tip very close to a surface. Electrons tunnel between the tip and the surface. By measuring the tunneling current, the microscope can map the surface with atomic resolution. This technology would be impossible without quantum tunneling. Tunneling also limits how small we can make transistors. As components shrink, barriers between different regions become thin enough for electrons to tunnel across them when they should not. This causes leakage current and energy loss. Engineers must design around quantum tunneling effects that were irrelevant in larger devices. Some researchers have proposed using tunneling for faster-than-light communication. The idea is to exploit the instantaneous or near-instantaneous nature of tunneling to send signals. But every careful analysis shows this fails. The randomness and uncontrollability of quantum mechanics always prevents actual communication. The universe blocks every attempt to exploit tunneling for messages. Quantum tunneling shows that particles can appear to cross distances without traveling through the space between. This sounds like teleportation or wormholes. In a sense, it is. The particle takes a shortcut through quantum probability space instead of moving through normal space. But the effect only works at tiny scales and cannot be controlled precisely enough for macroscopic applications. Still, tunneling is a reminder that quantum mechanics allows particles to do things that seem impossible classically. Barriers are not absolute. Distance can be crossed without traversing the path. These quantum effects might be hints of something deeper, some principle that could extend to larger scales under the right conditions. Every time you perform a quantum measurement, you affect the entire universe. This is not metaphor or exaggeration. The wave function is global. It extends across all of space. When it collapses, that collapse happens everywhere simultaneously. Measurement is fundamentally non-local. Think about what this means. You decide to measure a particle in your laboratory. That decision and its outcome instantly change the quantum state of entangled particles on the other side of the galaxy. Not after a delay, not with any signal traveling between them. The change is instantaneous and universal. This challenges our intuitions about observation. We think of observation as passive. You look at something and learn what it was doing. But quantum measurement is active. It forces the universe to crystallize into one specific configuration from many possibilities. And because quantum states are global, this crystallization happens everywhere at once. Different interpretations explain this in different ways. Copenhagen says the wave function is just information, so its collapse represents learning. But Bell's theorem proves the correlations are too strong for this explanation. Something physical must connect the particles. Pilot wave theory says the guiding wave is non-local. Many worlds says no collapse occurs, so there is no non-local effect. Each interpretation struggles with the same basic tension. The core problem is that quantum mechanics combines two incompatible features. On one hand, the Schrödinger equation is completely local. It describes how the wave function evolves smoothly in time, with each point in space only affected by nearby points. This evolution respects locality perfectly. On the other hand, measurement seems to be non-local. It projects the wave function onto a specific outcome instantly, everywhere. Some physicists think this tension points to something wrong with the theory. Maybe quantum mechanics is an approximation that breaks down when you really examine measurement. Maybe there is a deeper theory where measurement emerges naturally without requiring non-local collapse. This hope has driven research into alternative theories for decades. Other physicists think non-locality is simply a fact about nature. The universe has instant connections. We need to accept this and figure out how to incorporate it into our understanding. Perhaps locality is not fundamental. Perhaps space itself emerges from deeper quantum structures that are naturally non-local. Recent experiments have tested non-locality in new ways. In 2015, researchers closed the final major loopholes in tests of Bell's theorem. They showed conclusively that the correlations cannot be explained by any local hidden variable theory. The experiments used entangled particles separated by over a mile, with measurements made simultaneously in different locations. The results matched quantum predictions perfectly. These experiments also tested whether measurement choices could somehow be predetermined by hidden variables. The researchers used random number generators to decide how to measure each particle, and they made these decisions so close in time that no signal could travel between the locations. This ensured the measurements were truly independent, yet the quantum correlations remained. The verdict is clear. Non-local effects are real. Measurement of one particle instantly affects entangled partners anywhere in the universe. This is not an artifact of incomplete theories or experimental errors. It is how nature actually works. For faster-than-light travel, this suggests something important. The universe already has faster-than-light connections built into its quantum foundation. Maybe these connections are a hint. Maybe there are ways to amplify or exploit quantum non-locality to achieve macroscopic faster-than-light effects. Or maybe the restrictions on quantum non-locality, which prevent communication, are fundamental and will block all attempts to use it for travel. The vacuum of space is not empty, it seethes with energy. Virtual particles pop into existence and vanish. Quantum fields fluctuate wildly at the smallest scales. This vacuum energy is real and measurable. The Casimir effect proves it. The question is whether we can ever harvest it for propulsion. Several researchers have proposed ways to extract energy from the quantum vacuum. The most famous is the idea of a zero-point energy extractor. The concept is simple. The vacuum has energy. Find a way to lower the vacuum energy in one region while raising it elsewhere. The energy difference could power a spacecraft or other device. The problem is that lowering vacuum energy creates negative energy density. This is the same exotic matter needed for warp drives. So vacuum energy extraction and warp drives are closely linked. If you can do one, you might be able to do the other, but both face the same enormous technical challenges. Some designs propose using rapidly moving mirrors or boundaries to squeeze the vacuum. As the mirror moves, it changes the allowed quantum fluctuations in the space behind it. This creates a temporary region of reduced vacuum energy. The energy difference could theoretically be captured and used, but the forces involved are incredibly tiny. Scaling up to useful levels seems impossible with current understanding. Other concepts involve carefully shaped electromagnetic fields. Strong electric or magnetic fields can alter how virtual particles behave. This changes the local vacuum energy. By shaping the fields correctly, you might create propulsion. Some calculations suggest that oscillating fields could push against the quantum vacuum and generate thrust. NASA has investigated some of these ideas under the name quantum vacuum plasma thruster. The concept is to use microwave cavities to create asymmetric electromagnetic fields that interact with vacuum fluctuations. Early experiments claimed to detect anomalous thrust, but follow-up tests have been inconclusive. Most physicists remain skeptical. The fundamental issue is that vacuum energy extraction probably violates energy conservation if taken too far. You cannot get infinite free energy from nothing. There must be limits on how much vacuum energy you can extract before the system becomes unstable or requires more energy input than you get out. These limits might be so strict that vacuum energy propulsion is impossible in practice. Some theories predict that advanced civilizations might learn to manipulate vacuum energy at industrial scales. If you could create large regions of negative energy density, you could build warp drives and wormholes. The civilization would effectively be controlling the structure of space-time itself. This level of technology seems almost magical to us now. Another speculative idea involves using the expansion of space itself as an energy source. Space is expanding and dark energy drives that expansion. If you could couple to dark energy and extract its power, you would have access to an enormous energy reserve. This energy could potentially power faster than light propulsion or other exotic technologies. All of these concepts remain highly theoretical. None have been demonstrated in any convincing way. Most physicists think they will never work because they run into fundamental limits imposed by quantum mechanics and thermodynamics. But a few researchers continue to explore them, hoping to find a breakthrough. The one certainty is that the vacuum contains energy. Whether intelligence can ever exploit that energy for propulsion is unknown. If it is possible, it would revolutionize space travel. If it is not, we will need to find other paths to the stars. Travel faster than light and time breaks. Not gradually, not in subtle ways. It shatters completely. Cause and effect reverse. Future influences past. Logic itself collapses. Understanding why requires thinking carefully about what time actually is. In special relativity, time and space are linked. Different observers, moving at different speeds, disagree about time intervals and spatial distances. What you measure as 1 second might be 2 seconds for someone moving past you at high speed. This is time dilation, and it is proven fact. But everyone still agrees on cause and effect. All observers see causes preceding effects. This works because nothing travels faster than light. The light cone structure of space-time ensures causal consistency. Events inside your past light cone can influence you. Events outside cannot. Future is separate from past by a clear boundary. This boundary moves at light speed. Now imagine faster than light travel. You could reach events outside your light cone. Events that are in your future could suddenly be in your past. Different observers would disagree not just about time intervals, but about temporal order itself. What looks like forward time travel to you might look like backward time travel to someone else. Here is a concrete example. You travel from Earth to a star 10 light years away in just 1 year using faster than light propulsion. From your perspective, you traveled forward in time. You left in the year 2025 and arrived in 2026. But there exist reference frames moving at high speed relative to Earth where you arrived before you left. To those observers, effect preceded cause. If you could then travel back to Earth faster than light using the same technology, you could arrive back on Earth before you originally left. You would meet your past self. You could prevent your departure. The grandfather paradox emerges not from time travel but from faster than light travel combined with the relativity of simultaneity. This is why most physicists think faster than light travel implies time travel. They are equivalent. Any technology that allows one automatically allows the other. And time travel creates logical paradoxes that seem impossible to resolve within known physics. Some researchers have proposed consistency conditions that might prevent paradoxes. The Novikov self-consistency principle says that even if time travel is possible, events must arrange themselves to avoid contradictions. You cannot kill your grandfather because something always prevents it. The universe conspires to maintain consistency, but this feels unsatisfying. It suggests the universe has some mechanism for enforcing logical consistency that operates outside the known laws of physics. It makes causality into a fundamental principle that constrains what can happen, rather than emerging from the laws of physics. This is philosophically troubling. Another possibility is that faster than light travel does not lead to paradoxes, because many worlds is correct. When you travel backward in time, you enter a different branch of the wave function. You cannot change your own past because that exists in a separate branch. You can only affect other timelines. This eliminates paradoxes, but requires accepting the reality of countless parallel worlds. Alternatively, maybe closed time-like curves are simply forbidden by quantum effects we do not yet understand. Every time you try to create a time machine or travel faster than light, quantum mechanics interferes and prevents it. The universe has built-in protection against paradoxes. This would mean faster than light travel is impossible, not because of classical physics, but because of quantum restrictions. The bottom line is clear. Breaking the light barrier breaks time. Whether physics allows this is one of the deepest unsolved questions. If it is allowed, we need to completely rethink what time means and how causality works. If it is forbidden, we need to understand the mechanism that prevents it. What if space itself is not fundamental? What if distance and locality emerge from something deeper? This idea has gained traction in recent years as physicists explore quantum gravity and the nature of space-time. Several lines of research suggest that locality might be an approximation that breaks down at the deepest levels of reality. String theory provides one example. In string theory, particles are tiny vibrating strings. These strings can interact non-locally in certain situations. There are configurations where strings connect distant points in space directly without traversing the space between. The theory suggests that space emerges from the collective behavior of strings rather than being fundamental. Another approach comes from quantum information theory. Some researchers argue that entanglement is more fundamental than space. In this view, the geometry of space-time emerges from patterns of quantum entanglement. Distance between 2 points corresponds to how entangled they are. Strongly entangled regions are close. Weakly entangled regions are far apart. This idea is called the ER equals EPR conjecture. ER stands for Einstein-Rosen bridges, which are wormholes. EPR stands for Einstein-Podolsky-Rosen, which are entangled particles. The conjecture says these are the same thing. Every pair of entangled particles is connected by a microscopic wormhole. Space is stitched together by quantum entanglement. If true, this would explain quantum non-locality naturally. Entangled particles are not separated by space. They are connected through quantum wormholes. The faster-than-light correlations are not really faster than light, because the particles are touching through the wormhole, even though they appear far apart in ordinary space. Holographic principle points in a similar direction. This principle says that all the information in a volume of space can be encoded on the boundary of that volume. The interior is redundant. This suggests that three-dimensional space might be a projection or emergent property of something more fundamental that lives in fewer dimensions. Black hole physics supports this idea. The entropy of a black hole depends on its surface area, not its volume. Information that falls into a black hole is somehow encoded on the event horizon. The interior might not really exist as an independent region. Space inside the black hole could be an illusion created by quantum entanglement on the boundary. These ideas remain speculative and incomplete. Nobody has a full theory of how space emerges from quantum mechanics, but multiple independent approaches point toward the same conclusion. Locality and spatial separation might not be fundamental. They might emerge from deeper quantum structures. For faster-than-light travel, this has profound implications. If space is emergent, then perhaps the restrictions imposed by spatial separation are also emergent and not absolute. Maybe there are situations where the emergent description breaks down and you can access the underlying non-local quantum connections directly. This would not violate the fundamental laws of physics, because those laws might operate at the deeper level where space has not yet emerged. The speed of light limit would be a property of emergent space, not a fundamental constraint, just as the properties of water emerge from, but are not fundamental to the behavior of individual molecules. Whether intelligence could ever exploit this remains unknown. It would require understanding and manipulating the quantum structures that give rise to space itself. This is far beyond current technology or even current theory, but it suggests that faster-than-light travel might not be ruled out by fundamental physics, only by our current understanding of what is fundamental. We stand at a turning point in physics. The old certainties are crumbling. The speed of light seemed absolute, but quantum mechanics shows faster-than-light influences are real. Space seemed fixed, but general relativity shows it can bend and stretch. Time seemed universal, but relativity proves it is relative. Every foundation we thought was solid turns out to be flexible. The experiments are definitive. Bell's tests prove quantum non-locality beyond any reasonable doubt. Measurements of cosmic expansion prove space can move faster than light. The Casimir effect proves negative energy exists. These are not speculations. They are established facts that any complete theory must explain. Yet we still lack that complete theory. Quantum mechanics and general relativity work brilliantly in their own domains but contradict each other at deep levels. Quantum mechanics is non-local. General relativity is local. Both cannot be completely correct as currently formulated. Something has to give. The search for quantum gravity aims to resolve this tension. String theory, loop quantum gravity, and other approaches try to unify the quantum and gravitational worlds. These theories suggest that space-time itself is quantized at the smallest scales. Below the Planck length, distance loses meaning. Space and time might not exist as continuous entities. If space-time is emergent from quantum mechanics, then the restrictions we associate with space might not be fundamental. The speed of light limit might apply only to the emergent description, not to the underlying quantum reality. This opens the door to faster-than-light phenomena without violating the true fundamental laws. But we need more than theory. We need experiments that probe the boundary between quantum mechanics and gravity. We need tests that explore space-time at extreme scales. We need observations that distinguish between competing theories. This work is underway, but progress is slow. The relevant energy scales are far beyond what we can reach directly. Some researchers hope that quantum computing will provide insights. Quantum computers exploit entanglement and superposition at macroscopic scales. As these devices grow more sophisticated, they might reveal new aspects of quantum mechanics that point toward faster-than-light possibilities. Or they might reveal fundamental limits we have not yet discovered. Others look to astrophysics. Observations of black holes, neutron stars, and the cosmic microwave background might contain clues about quantum gravity. Strange phenomena in extreme environments might show us where our current theories break down and hint at what comes next. The practical implications for space travel remain distant. Even if faster-than-light travel is possible in principle, the engineering challenges are staggering. We need to manipulate exotic matter, control quantum fields, or somehow tap into the emergent nature of space-time. None of this is within reach of current or near-future technology, but the history of physics teaches us humility. Things that seemed impossible often turned out to be merely difficult. Heavier-than-air flight was impossible until it was not. Nuclear energy was theoretical until it was not. Quantum computing was a fantasy until it was not. Each breakthrough seemed miraculous in hindsight, but inevitable once achieved. Maybe faster-than-light travel will follow the same pattern. Maybe centuries from now, humans will look back at our current certainty that nothing can exceed light speed with the same amusement we feel reading about scientists who proved flight was impossible. Maybe the universe is stranger and more permissive than we imagine. Or maybe the speed of light really is absolute, and faster-than-light travel will forever remain a dream. Maybe the universe designed causality protection into its deepest laws specifically to prevent paradoxes. Maybe locality at the macroscopic scale is unavoidable, no matter how non-local quantum mechanics might be. We do not know yet. The experiments are still running. The theories are still evolving. The questions remain open. But one thing is certain. The universe has already shown us that faster-than-light phenomena exist. Quantum entanglement is real. Cosmic expansion exceeds light speed. Negative energy exists. These facts demand explanation and might contain the seeds of revolution. The speed of light may not be the final barrier after all. It might just be the first one we learn to measure. Beyond it could lie realms of physics we have barely begun to imagine. The journey to discover them has already begun. Particles can travel faster than light. This is happening right now in nuclear reactors and particle accelerators around the world. The key is that light speed depends on the medium. In empty space, light travels at 186,000 miles per second. In water, light slows to about 140,000 miles per second. In glass, even slower. But charged particles like electrons can be accelerated to speeds greater than light travels in those materials. An electron moving through water at 160,000 miles per second is going slower than light in vacuum, but faster than light in water. This creates a shock wave of light called Cherenkov radiation. Think of a jet breaking the sound barrier. Sound travels at around 760 miles per hour through air. When a jet exceeds this speed, it creates a sonic boom. The aircraft outruns the sound waves it produces. They pile up and form a shock wave. Cherenkov radiation is the optical equivalent. The particle outruns the light waves it produces in the medium. The effect produces a characteristic blue glow. Nuclear reactors often have pools of water surrounding the reactor core for cooling and radiation shielding. When radioactive decay products shoot through this water faster than light travels through water, they emit Cherenkov radiation. The pool glows with an eerie blue light. This is direct visual evidence of particles exceeding the local light speed. Soviet physicist Pavel Cherenkov discovered this radiation in 1934 while studying radioactivity. At first, he thought it might be fluorescence or some chemical reaction, but careful experiments showed it was something new. The light came directly from particles moving through the medium faster than light could. Scientists quickly realized they could use Cherenkov radiation as a detector. When a high-energy particle passes through water or ice, it leaves a trail of blue light. Photodetectors surrounding the medium can capture this light and reconstruct the particle's path. This technique led to huge underground detectors filled with thousands of tons of ultra-pure water. The ice cube detector at the South Pole uses a cubic kilometer of Antarctic ice as a detector medium. When neutrinos from space pass through Earth and interact with the ice, they produce charged particles that emit Cherenkov radiation. The blue light flashes through the ice and gets detected by sensors frozen into the glacier. This is how we observe neutrinos from distant cosmic events. Cherenkov radiation proves that exceeding light speed in a medium causes observable physical effects. The particle creates a cone of light behind it, similar to the wake behind a boat. The angle of this cone depends on how much faster than light the particle is moving. Measure the angle, and you can calculate the particle's speed. But none of this violates relativity. The particles are still moving slower than light in vacuum. Relativity only forbids exceeding the vacuum speed of light. Local light speed in materials is slower due to interactions between light and atoms in the medium. The particles exploit this difference. Still, Cherenkov radiation shows what happens when you push past a local speed limit. The universe responds with radiation and shock waves. If something could truly exceed the vacuum speed of light, the consequences would be far more dramatic. Space itself might ring like a bell. In September 2011, physicists made an announcement that shocked the world. Neutrinos appeared to be traveling faster than light. The Opera experiment in Italy had measured neutrinos arriving 60 nanoseconds earlier than they should if they traveled at light speed. This was barely faster, only about 25 parts per million above the speed limit. But any violation would overturn a century of physics. The experimental setup was impressive. Scientists at CERN in Switzerland created intense beams of neutrinos by smashing protons into a target. These neutrinos traveled through Earth's crust for 450 miles to the Opera detector deep underground in Italy. The journey should take about 2.4 milliseconds at light speed. But the measurements showed the neutrinos arriving early. Not by much. 60 nanoseconds is 60 billionths of a second. But the measurement was precise and repeated thousands of times. The statistical significance was overwhelming. Either neutrinos were breaking the speed limit or something was wrong with the experiment. The announcement created a media frenzy. If true, this would be the biggest physics discovery in generations. Faster than light particles would force us to rewrite special relativity. Causality might be violated. Time travel could be possible. The implications were staggering. Most physicists were skeptical. Extraordinary claims require extraordinary evidence. The speed of light had been tested countless times. Every experiment confirmed Einstein's prediction. It seemed far more likely that the opera team had made an error than that relativity was wrong. Scientists worldwide scrutinized the experiment. How did opera measure the neutrino travel time? They used GPS satellites to synchronize clocks at CERN and at the detector in Italy. They measured the distance using surveying equipment. They recorded exactly when the proton beam hit the target and when neutrinos were detected. The timing had to be incredibly precise to see a 60 nanosecond effect. Within months, problems emerged. The fiber optic cable connecting the GPS receiver to the timing equipment was not properly secured. This introduced a delay of about 60 nanoseconds. When the connection was fixed, the faster-than-light effect vanished. Additional checks revealed that an oscillator used for timing was also slightly off. These two errors combined to create the illusion of faster-than-light neutrinos. In February 2012, Opera announced they had found the mistakes. The neutrinos were traveling at exactly light speed within measurement error. There was no violation of relativity. The speed limit remained intact. The experiment had been wrong due to equipment problems. The episode was embarrassing for the collaboration, but ultimately a triumph for science. The researchers had been careful and transparent. They announced their result, but emphasized they needed independent verification. Other experiments checked and found no faster-than-light neutrinos. The error was discovered and corrected. This is how science is supposed to work. But the incident revealed how desperately physicists wanted faster-than-light particles to be real. For a few months, the possibility hung in the air. Maybe the speed limit could be broken. Maybe relativity was incomplete. The disappointment when the effect vanished was palpable. Yet the opera error reminds us to be skeptical of extraordinary claims. The speed of light has been tested exhaustively. Breaking it would require overwhelming evidence from multiple independent experiments. One result from one detector with timing uncertainties is not enough. The universe guards its secrets carefully. There is a type of speed that can exceed light speed without violating relativity. It is called phase velocity, and it describes how fast wave patterns move. This is different from group velocity, which describes how fast information or energy moves. Phase velocity can be faster than light. Group velocity cannot. Imagine watching waves on the ocean. Individual wave crests move at a certain speed. That is phase velocity. But if you put a cork in the water, it bobs up and down without traveling far. The water itself does not move with the wave crests. The energy and information travel at a different speed. That is group velocity. In certain materials and situations, phase velocity can exceed light speed dramatically. Laser pulses passing through specially prepared atomic vapors have shown phase velocities hundreds of times faster than light. The peaks of the wave pattern race ahead at superluminal speeds, but no information travels faster than light. You cannot use phase velocity to send messages. Here is why. To send a message, you need to modify the wave somehow. Turn it on or off. Change its amplitude or frequency. These modifications travel at the group velocity, which always obeys the speed limit. Think of a stadium doing the wave. People stand up and sit down in sequence. The wave pattern moves around the stadium faster than any person runs, but no person travels with the wave. No information gets transported. It is just a pattern effect. Phase velocity works the same way. Some experiments have produced even stranger results. In 1999, researchers sent light pulses through cesium gas and measured them exiting before they entered. The peak of the pulse emerged from the far side of the gas chamber before the peak entered the near side. This sounds like time travel or faster than light transmission, but careful analysis shows otherwise. The pulse has many frequency components. Different frequencies travel at different speeds through the gas. The leading edge of the pulse, which travels at the group velocity, still obeys the speed limit. What exits early is a reconstructed peak formed by the overlapping frequency components. No information travels faster than light. You could not use this effect to send messages backward in time. These experiments teach us something important about what the speed of light actually limits. It is not wave patterns or mathematical peaks. It is information, energy, and causality. Anything that could be used to influence cause and effect must obey the speed limit. Everything else is negotiable. This distinction matters for understanding quantum mechanics. When an entangled particle is measured and its partner responds instantly, no information travels between them. The correlation exists, but you cannot exploit it for communication. The phase of the quantum wave function might change superluminally, but the group velocity of any measurable effect remains subluminal. Some physicists have proposed exploiting phase velocity effects for faster than light communication. Maybe there is a clever trick that converts phase velocity into useful information transfer. But every attempt has failed. The universe seems to have built-in protection. Phase velocity can exceed light speed, but it cannot carry information. The two types of velocity are fundamentally different. This separation might be a clue about deeper physics. Maybe the speed limit only applies to certain aspects of reality while other aspects can exceed it. Maybe information is what really matters, and speed is just a consequence of how information propagates. Understanding this distinction might be key to unlocking faster-than-light possibilities. In 1999, physicists performed an experiment that seems to show the future affecting the past. It is called the delayed choice quantum eraser, and it remains one of the most mind-bending demonstrations in quantum mechanics. The experiment suggests that decisions made now can change what happened in the past. Start with the classic double-slit experiment. Fire photons at two slits. Each photon goes through both slits simultaneously, creating an interference pattern on the detection screen. But if you measure which slit the photon went through, the interference vanishes. The act of measurement changes the photon's behavior retroactively. The quantum eraser adds a twist. After the photon passes through the slits, place detectors that could tell you which path it took. This destroys the interference pattern. But now add another step. Before looking at the which path detectors, pass their results through a quantum eraser that scrambles the information. When you erase the which path information, the interference pattern comes back. Here is where it gets strange. You can delay the erasure until after the photon has already hit the screen. Make the decision whether to erase the which path information long after the photon has been detected. According to the experimental results, your future decision seems to affect what pattern appeared in the past. If you choose to erase the information, the photons that already hit the screen show interference. If you choose not to erase, they show no interference. Your choice now appears to change what happened then. This looks like retrocausality, with the future influencing the past. But there is a catch that saves causality. You cannot see the effect until you correlate the data. The photons hitting the screen look random either way. Only when you sort them based on the eraser results do you see that one group has interference and the other does not. You need information from both measurements, present and future, to see anything unusual. This means you cannot use the quantum eraser to send messages to the past. You have no control over which photons end up in which group. The sorting happens after the fact. You can see retroactive effects in the data, but you cannot exploit them for communication or causal manipulation. Still, the experiment suggests something profound about time in quantum mechanics. The photon does not have a definite history until all the measurements are complete. Its past is indeterminate, waiting for the future to crystallize it into one specific narrative. Past and future are not as separate as we assume. Some interpretations of quantum mechanics embrace retrocausality explicitly. The transactional interpretation, proposed by John Cramer, describes quantum events as handshakes between waves traveling forward and backward in time. The absorber theory suggests particles reach back in time to negotiate with their source before being emitted. These ideas remain controversial. Most physicists prefer interpretations that preserve normal causality, even if they require accepting other strange features like non-locality or many worlds. But the quantum eraser experiments show that reality is deeply weird no matter which interpretation you choose. For faster-than-light travel, retrocausality offers a potential loophole. Maybe time is not as rigid as we think. Maybe cause and effect are more flexible at the quantum level. If so, faster-than-light travel might not create paradoxes, because the past could adjust itself to maintain consistency. The universe might have mechanisms we do not yet understand that prevent logical contradictions. Or maybe these quantum effects cannot scale to macroscopic systems. Maybe retrocausality is confined to individual particles and cannot be amplified to affect human-scale events. The boundary between quantum and classical physics might prevent us from ever exploiting these strange effects practically. Black holes create a puzzle that has tormented physicists for decades. Information that falls into a black hole seems to disappear forever, but quantum mechanics says information cannot be destroyed. This contradiction between general relativity and quantum mechanics is called the information paradox, and its solution might require faster-than-light connections. When matter falls into a black hole, it crosses the event horizon and is lost to the outside universe. No light or information can escape from inside. To an outside observer, the infalling matter vanishes completely. The black hole grows slightly in mass, but all the detailed information about what fell in seems erased. Stephen Hawking made the problem worse in 1974. He proved that black holes emit radiation and slowly evaporate. After enough time, the black hole vanishes entirely. But Hawking radiation appears to be completely random, carrying no information about what fell in. This means the information is truly destroyed. Quantum mechanics forbids this. Information must be conserved. For decades, physicists debated how to resolve the paradox. Some argued that information escapes in subtle correlations in the Hawking radiation. Others suggested it remains trapped at the event horizon. Still others proposed that black holes leave remnants behind when they evaporate, preserving the information. Recent work suggests a radical solution. The information might be encoded non-locally. When something falls into a black hole, its information gets entangled with the Hawking radiation through quantum connections that span the event horizon. The information exists simultaneously inside and outside the black hole through faster-than-light quantum correlations. This idea connects to the ER equals EPR conjecture mentioned earlier. Entangled particles might be connected by microscopic wormholes. For black holes, this means the interior and exterior are linked by quantum wormholes. Information can exist in both places at once, without traveling between them at subluminal speeds. Another proposal involves firewalls. The event horizon might not be empty space, but a wall of high-energy particles created by quantum effects. These particles would destroy anything trying to cross. Information would never actually enter the black hole. It would be released back into Hawking radiation at the horizon through non-local quantum processes. The firewall idea is controversial because it violates the equivalence principle. Someone falling into a black hole should not notice anything special at the event horizon. They should fall smoothly across. A firewall would make the horizon a physical barrier, changing the nature of gravity in ways that contradict general relativity. All proposed solutions to the information paradox involve some form of non-locality or faster-than-light effects. Either information escapes through quantum entanglement, or it gets encoded on the horizon through holographic principles that treat space as emergent, or it remains connected to the exterior through quantum wormholes. This suggests that understanding black holes requires accepting non-local connections. Space and time might break down near black holes in ways that permit faster-than-light information transfer, not through normal channels, but through quantum entanglement. and the holographic structure of space-time. For faster-than-light travel, this is encouraging. If nature already uses non-local effects to resolve paradoxes at black holes, maybe these effects could be exploited more generally. Maybe the extreme conditions near black holes reveal possibilities that exist everywhere but are normally hidden. Advanced civilizations might learn from black hole physics how to manipulate quantum connections for communication or travel. But black holes also warn us about the dangers. Their extreme gravity crushes everything. The tidal forces would tear apart any spacecraft. Even if faster-than-light effects occur near black holes, extracting useful technology from that environment seems impossible. We would need to understand the physics well enough to recreate it in controlled laboratory conditions. That understanding remains far beyond our current theories. Imagine waking up one morning to news that scientists have achieved faster-than-light travel. Not in theory, not in principle. Actually done it. A spacecraft left Earth, traveled to Alpha Centauri, 4 light-years away, and returned in less than a year. Everything changes, instantly, completely, forever. The first impact would be philosophical. For over a century, we have built our understanding of reality on the foundation that nothing exceeds light speed. Every textbook, every theory, every experiment assumed this was absolute. Breaking that barrier would mean our most fundamental physics is incomplete. We would need to rewrite quantum mechanics, relativity, or both. The implications would ripple through every branch of science. But the practical effects would be even more staggering. The galaxy would suddenly be accessible. Stars that seemed forever beyond reach would become destinations. We could visit thousands of star systems within a human lifetime. The isolation that has confined humanity to one tiny planet in an empty cosmos would end. We would become a multi-system civilization almost overnight. Economics would transform. Resources from asteroids and other planets are abundant, but currently unreachable in practical timeframes. Faster-than-light travel would make interstellar mining viable. Elements rare on Earth but common elsewhere could be imported. The resource limitations that drive conflict and scarcity would dissolve, or new conflicts would emerge over who controls the new resources and territories. Politics would fracture and reconfigure. Earth governments would struggle to maintain authority over colonies light-years away. Even with faster-than-light travel, ruling an interstellar empire would be nearly impossible. Colony worlds would develop their own cultures, economies, and governments. Humanity would diversify into countless variations, adapting to different worlds with different conditions. The search for extraterrestrial intelligence would accelerate dramatically. We could visit potentially habitable planets directly instead of waiting decades or centuries for radio signals. We could explore thousands of star systems looking for life. Either we would find we are not alone, which would change everything about how we see ourselves in the cosmos, or we would confirm we are alone, which would be equally profound and troubling. But there would be dangers. Faster-than-light travel might enable time travel. This could create paradoxes, or allow manipulation of history in ways that threaten causality itself. Safeguards would need to be developed. Laws governing time travel would become as important as laws governing any other technology. How do you regulate something that can affect the past? Military implications would be severe. Faster-than-light weapons could strike anywhere without warning. Defenses would be nearly impossible. The weapons could arrive before you detect them leaving the enemy location. Deterrence and strategy would need complete rethinking. Wars could be won or lost in seconds across interstellar distances. There would be winners and losers. Nations or corporations that develop the technology first would have enormous advantages. They could claim territory, exploit resources, and establish dominance before others catch up. This could create inequality on a galactic scale. Or it could distribute wealth and opportunity so widely that scarcity becomes obsolete. Culture would explode in diversity. Every colony world would develop its own art, philosophy, and way of life. We would encounter human societies as alien to each other as any extraterrestrial civilization. This could enrich humanity with countless perspectives and innovations. Or it could fragment us into incompatible groups that lose their common identity. Religion and spirituality would face challenges. Many belief systems are grounded in Earth-centric views of creation and humanity's place in the cosmos. Becoming an interstellar species would force reconsideration of these teachings. Some faiths would adapt. Others might resist or reinterpret their doctrines. New spiritual movements would emerge to make sense of the expanded human experience. The very meaning of being human would shift. We evolved on one planet under specific conditions. Spreading across the galaxy would expose us to different gravities, different radiations, different selection pressures. Over time, humans on different worlds would diverge genetically and culturally. We might become multiple species descended from a common origin. The unity of humanity would be tested by our cosmic expansion. All of this assumes faster than light travel is possible. It might not be. The universe might have hard limits we cannot overcome. But the fact that we can now seriously discuss these possibilities shows how far physics has come. We know faster than light influences exist in quantum mechanics. We know space can expand faster than light. We know negative energy exists. The pieces are on the table. Whether we can assemble them into working technology remains the question that will define the next century of physics.